and then the dies come on again. So that's very tricky. But what we can do, so this solve by iteration I put is not in the exam. Now it is in the homework, I believe, just to get you really thinking about the mathematics of it. But it's not in the exam. What we'll do is do some approximations, and the approximation is to just use a half period for the decay. So in other words, we'll say it'll decay from the peak of this sine wave all the way through to the half period down here. And now, if that's a fairly flat, if that's a fairly level line, that approximation is quite good. If that line starts to get sort of steep, it's going to come further down the sine wave, and it's going to get worse and worse as time goes on. But you know what? It's an approximation. It gets us moving. We can use the LT spice later, and it does get us, moving in terms of designing a circuit. And this is the difference really between design and analysis and sort of simulation. You can think of analysing a circuit, designing a circuit, simulation. They're all different activities. Design, you want some simple design equation. Analysis, you want to see, how is that sensitivity around that design equation. Simulation kind of gives you an accurate answer. It's like the ultimate calculator, isn't it? And of course, you can do sensitivity, you can do analysis in inverted commas with a simulator if you realise what you're doing. But you need to think clearly about this stuff, and this does crop up. So the usual simplifications then, a linear decay of the capacitor voltage from one peak for a whole half cycle, so that's pi by 2, and then that sort of helps quite a lot, because then we can find our ripple, and it's the ripple we're interested in the end. So our ripple then is starting at the peak, going for one half cycle of the exponential decay from the peak, because it's not actually from the peak, right? So it's not from there, but we're making these assumptions, right? And we then know that it's a half cycle to 1 on 2f. So we get out this very nice equation here. And this is what I would call a design equation. That gets you most of the way to your sort of initial design, and then you can start to embellish on that and sort of say, well, actually, maybe we should use this chip, because at the moment we're using a big capacitor to get a nice light out of this thing. Maybe we should let it ripple more, in which case a small capacitor means more ripple. So we could let it ripple a bit more, but then we can use this chip. So now I'm saving money on a capacitor, and I'm spending money on a chip. Why is that possibly a good idea? Capacitors, particularly electrolytic capacitors, don't have a very good lifetime. And you want these things to last, 5 years, 10 years, not just to have 2 years, which this one lasted for me, but that's I want to see what the fault is in there. But you want them to last a long time, because then the payback on the electronics complexity, beats the energy saving beats the cost of the cost of the electronics. You're saving, and it says on the boxes, right? Is it? I was going to say, you guys, maybe you've never bought one of these things in your life, but it says on the box, So next time you're in Dollarama or Dollar Tree, pick up one of the boxes and just read what it says on the side. It'll say something like 9 years life. It's going to save you $5 or something. Interestingly, Dollarama is getting a bit pricey in Dollarama actually, so I was quite pleased to pick up some nice ones in Dollar Tree, less than half the price of Dollarama. Dollarama's very high quality, by the way. They do dimmable little spots, which is very unusual, and they're very expensive if you buy them other places. But anyway, there we go. Advertising moment over. I should do YouTube and get money off Dollarama, shouldn't I? Anyway, okay, let's stop there. Let's watch a video, which is more of me. maybe I'll put it single. Well, don't know how to do that anymore. Okay, I'll
Is that
try
it?
it.
Dr. Electronics.
Smoothing, full bridge rectified with capacitor smoothing, as shown in the slide on my left. And I've got a little demo here. We find full bridge smoothing in a compact fluorescent light, so I brought in a light here. I should check the on. So here's a lamp.
I do got these demos filmed because I realised one day the university's going to watch me having live electricity, and it's English electricity or European 230 volts, and they're going to go tell me I can't do
Take
it
it to
anymore.
pieces, and you can see in here there's about 8 diodes, actually 4 of which are the full bridge rectifier, and then we have the last.
So it's a bit old, so I apologise for that.
That's
There's
the
electricity.
smoothing. That happens to be, in this case, 2.8 microfarads, 400 volts, coming straight in off the mains electricity. So I've taken that to pieces. I brought in a couple of wires either side that capacitor so I can connect to it. And we should be able to measure some voltage. And I've added some resistors here so we can measure the current of the main supply. So, just check that this is going to work. Okay. Right, we're going to measure voltage. We're going to use these rather special differential probes. This is mains voltage. Don't do this at home, it's very dangerous. These differential probes are designed especially for this type of activity. So there's no earth, there's no ground, and you can just connect across.
By the way, when I do LT Spice and I click on one and it's red, and then I drag down to black, that's the differential probe. And notice they literally, they're red and black. They're not so expensive these days, but they're usually a few $100.
Another pair on my current. Got my resistors here. And hopefully we can put that in. And we have light. And we have our traces up on the scope now. So over here we have the voltage waveform. Notice where the ground is. Ground is down here. So we've got our main rectified voltage with some ripple on it, just as we had in the lecture notes. And you can see during this period here, we're charging. And here's the mains current, a small current charging through there, and then that goes off, and we simply linearly discharge as the capacitor voltage decays. You'll see some interesting features here. It jumps up almost instantaneously when this voltage on the capacitor hits the mains voltage, the rectifier comes on, and the current jumps up rapidly, and then drops off as the capacitor is charged up. And it's supplying a low current a little bit there too. During this period, the second period, the low current is supplied entirely by the capacitor, that big capacitor there. So what we can see here then is that there is no DC in this. Notice where the ground is set here. So we have no DC in the mains current there. That's a good thing. We want AC current. We don't want any DC in the mains. And that's why we have to use a full wave bridge or something similar on the compact fluorescent light. These are proliferated all around the building and more or less the world now. So that's very important to have a symmetrical AC waveform. The smoothing is reasonably okay, but it does have a big ripple on it. But from the point of view of our light, you'll see the light is very smooth. There doesn't seem to be any ripple in the light output. So we can say that this is smooth effectively enough. So this is part one of our compact fluorescent circuit. The second part we will look at how the rest of the circuit produces the light. We can do a little experiment just by checking another tube. Here's one out of the box, and brand new, unused, very unusual looking one. We can just put that in, just check on the plug. So we'll just test the current on that one. same sort of current this time, showing the big spikes of current. Now that's a slightly higher power and has a bigger current. What we can also say is that we are drawing these spikes of current off the main supply. So something else we can do is just look at the actual waveform from the mains. So I'll unplug again, keep myself safe and alive. We'll come in.
I've forgotten about this bit.
Just check the mains voltage. So I'll just bring that trace 2 up a bit. And down a little bit. Let's see our mains voltage.
That captures.
And there we can see that the mains voltage is rather flat topped during the charging period, but it coincides with taking current out of the peak of the supply on both sides, and therefore it has upset the mains voltage a little bit, simply because of the impedance of the supply, and that's the mains voltage coming into this bit.
So actually, if you look at that closely, you see the flat top actually doesn't quite coincide with that spike. So it's not the LED lighting that's doing that, it's actually the three-phase, probably the three-phase rectifiers that are around the system. But that's pulling current, these bits of current. There might be other things as well, but it's pulling bits of current out of the supply and it's flattening down the top, which is, you know, pretty unpleasant actually, not good for the supply. And you know, this does cause problems. SFU Burnaby sometimes has problems, YVR has problems sometimes with harmonics from all these rectified loads and what have you. So there we go. So what's the, you know, obvious sort of takeaways from this? You know, it's cheap, it's cheerful, saves energy, but it does have a bit of a drawback for us. I pulled up this particular slide because you can see over here, here's this instantaneous current, okay? It's that omega C cos omega T root 2V. And where is that? Well, over on here, of course, it's, you know, some way up the sine wave, right? So it has got that specific value. So that current goes piling into that capacitor pretty fast. Obviously, it's a differential. It's a differential of that sine wave at that point. Okay, so there's nothing to stop that current going quickly. Why do I mention that here? I want you guys to go with the maths, you know? Don't sort of say, oh, that can't do that. Think about the maths, what the maths is telling you. You know, you've sketched it, you've simulated it, whatever you've done, think about what's happening. So again, that's a reason for having a smaller capacitor, because then your spike current is smaller, which is nicer to your diodes. You're likely to get a longer lifetime. So now we're doing sort of design engineering, proper design. You know, you don't have to, I'm not expecting you to do that in the exam, but I'm trying to distinguish between, you know, what are good equations to think about and, you know, what's sort of meaningless. I try and ask questions which reflect the good things to think about. So a peak diode current on a capacitor smooth bridge rectifier would be a typical type of question to think about, okay? And of course that diode current also has the sine omega T upon R. It has the resistive load component as well. Anyway, well, I hope that bit was a bit of fun. Let's say some of this is fine. Let's go through here. The next thing to think about is, well, how about I put in, you know, I've talked about an integrated circuit. We talked about that. That's fine. You know, how about I put in a bit of line inductance? Because the line inductance will kind of drop the volts and stop that big spike of current. That's, you know, could be quite a nice thing to do. And that is often done on three-phase rectifiers. It may be done on a very big capacitor smooth job here. It's quite nasty to analyse because you've now got that inductor impedance to think about. But you can see that what's happening in the circuit. There's my VD as I suppose the diode breach voltage. So I've shown D1 and D2 on. I might have misread it there. There's an angle that looked like D3. There's D1 and D2. You've got the inductor there. That's when the diodes come on. We can work out how that current is going to build up. Nasty to analyse, so not in the exam at all. We just did that. Think about the harmonic distortion. We can, again, we can come out with this total harmonic distortion. Pretty nasty, really. Cross frequencies give 0. That was what I was proving in here. I need to carry on proving that because my sketch doesn't seem to quite tie up with my volts and my current. Has to be something in there. That's interesting, isn't it? Yeah. Need to think about that. But sometimes you can't argue with the maths. I may be misinterpreting the diagram here. But we got. That's right. That's what we said. V sine omega t with the I sine omega t. Oh, of course. You guys should have been helping me here. You've got two frequencies. So what do you get? You get the sum and the difference. So you get a 4 omega t and a 2 omega t. So both of them will be sine waves. So your S is both of them sine waves. There's no average power. Okay? Because you get the sum and difference frequencies there. Do you remember that? Adding modes and things like that sort of thing. No? A bit rough. It's not in my formula book, and I remember I wanted to add that formula to my formula book because it's it's not there. Sine A, sine B. I suppose it is. Oh no, I did add it in. I added it in rather late. Which one am I on? Source. DocuCam. It is in the formula book. You'll notice it's been a late addition. I need to retype it. So if that's your omega t, that's your 3 omega t, you get the 1 minus 3, which is minus 2, and then 1 plus 3, which is 4. So both of them are sine waves. There's no average power. I will think a bit more about the sketch. What I'll do is I'll do it in LT Spice, because that's easy, right? LT Spice will sketch it for me another time. Average power, 0 power in the harmonics. So what we really want then is we want that fundamental value of, to get the actual power out, we need the fundamental value of the S1, the current in the source, which is the fundamental value, S1, and we need that cos phi angle, the power factor angle, but with displacement as well. Okay, there we go. Yes, there we go. Cross frequencies give 0, so that's fine. That's all good. We need we do have a displacement angle because it's pushed. I've lost it. I lost the YouTube. But it's pushed to one side, so there's a displacement angle. There's also the fundamental. We've got to find the fundamental. Okay. Why are we interested in that? Because of the losses in the wires and so on. Okay, before we end, I'm just going to introduce the three-phase system so that we can continue with it next time. I've shown it here, the LT Spice. What do we know about a three-phase system? It's symmetrical. Let me just find my pointer. There we go. So look at these voltage. In fact, we're going to do it with the laser pointer. It's an ideal version of it as well. So you've got these three sources. Notice the angle is at the end here when you define a voltage source in LT-Spice. So this is the angle in degrees, 120 degrees, 240 degrees. Oh, hang on. Okay, 0, 240 and 120, which probably is those ones. Why have I got... Oh, sorry, there's the 0, 1 up here. So if you put nothing in there, it just assumes 0. Okay, I should have typed it out fully to make my point. So we've got the three sine waves symmetrically separated. We can connect loads to it in different ways. Sometimes we connect the loads in what we call a star. So that's what we've got happening here. So we've got this floating star point there. So this again looks like the Mercedes star, and that's your star point in the middle. Again, everything's symmetrical here. What we might find is that we've got some power factor going on here. So what we would often do is put in capacitors across the supply to provide some reactive power to compensate for inductive type reactive power over here. We've also got inductive reactive power here as well, typically. Can't remember what I was doing with these particular currents, but doing something. But the idea is that everything is balanced, all perfectly balanced. And then we end up with a very nice system with absolutely dead flat power. Now I'm going to show that next time. What I want to do is just sort of quickly go through the diode bridge, widely used for motor drives and all sorts of systems, but a lot of motors. Think of factories, think of SkyTrains, think of all of these things. The diode bridge producing a DC link that then goes to some load, which is probably an inverter and so on, which we'll get to next. But let's stay where we are for a moment. Notice the numbering scheme, 1, 3, 5, so odds at the top, evens at the bottom. Now we're in three-phase, we need to be a little bit craftier with our numbering. So you'll notice we're going to be good coders, so we're going to make them three different. So D1 at the top, D4 at the bottom, D3 at the top, D6 at the bottom, D5 at the top, D8 at the bottom. Kind of 8. So we're back to 2 again, right? So a nice scheme there. Then we can know that our pattern is going to be a nice simple pattern to describe. How else are we going to think about this? It's actually quite useful because you've got so many potential, you've got 6 potential current paths. Because of that, it's quite useful to think about the bridge in 2 halves. So we'll just repeat these things down here. They're voltage sources, so we can kind of pretend that we've got 2 of them, and we've sort of separated out the positive half of the bridge and the negative half of the bridge. So that's quite nifty. Why can I do that? There's not a connection across here. I've shown it dotted, but we can say that we've also symmetrically split the load in its halfway point as well. Having done that, we can then define this as a point N, and it's all symmetrical, so we've got a sort of point N over here, a point N over there, which is pretty nice. You could say that's neutral. Over here it is neutral, over here it's not really, but it's not at all, because it's not actually connected. But we're just exploiting the fact that it's all symmetrical. So then we can say, well, how are we going to analyse that? Well, use the idea of voltages. The highest voltage has to win. So AN is the highest, the other 2 are lower. BN is the highest, CN. So the highest voltage winning takes us across there. And that tells us that we go D1, D3, D6, D5. D1, D3, D5, D1, D3, D5, and so on. The other half, Same sort of thing, except it's the lowest voltage wins, because the diode's the other way around. So we've got D4, D6, D2, or I could have done it D2, D4, D6, D2, D4, D6, and so on. Then you put the two halves back together, like that. What do you notice? You notice they're out of sequence by, out of phase by, I'm going to get this right, 60 degrees. How do I know it's 60 degrees? Because one cycle is 3 of those bumps, that's 360. So this is 120, so halfway is 60. So now I've got a system where I've got, starting from, let's start from here, I've got D1, D6, D1, D2, D3, D4, D5, D4, D5, D6. Now it's a subtle code. Only one changes at a time. But now our difference across the load is this beautiful ripple, very low ripple AC waveform like that, DC waveform like that. So very nice. The three-phase bridge, absolutely fantastic. Very low ripple, even without capacitors, this is low ripple. So, you know, really, really nice. Yeah, we've done that. Oh, yeah. When you do that, by the way, it's what we call the line voltages. I'll come back and go over this again next time. Do it with respect to the simulation. Notice the coding. 6 different unique codes down there. 1, 6, 1, 2. So notice the 1s are on for a third of the cycle, the 3s are on for a third of the cycle, the 5s on. Same at the bottom, but displaced by 2. So that's quite an interesting dance. I don't know what dance you call that with 3 partners. There probably is a dance. There's got to be a dance, doesn't there? 3 partners, and you know, changing partners and all that sort of stuff. Anybody know? I have no idea. But there's bound to be one, right? 3 partners, and you swap partners, and you do your dance, and probably from about 1850 or something like that, or even earlier. You know, but it's a very nice little repetitive pattern. With, you know, this nice interchange, pretty cool, really. As it says, this book's pretty smooth already. Very common method above 10 kilowatts. So it's, you know, pretty nice sort of system. Now in Europe and in many countries, Vietnam, whatever, you've got 3-phase commonly. In North America, because it's certain bits of it, particularly British Columbia and bits of northern Canada and so on, we don't always have 3-phase. So sometimes we've got to work with just single phase. But this is very nice. I want to get the average voltage out. Well, that's very easy. I just integrate one of those 6 cycles, because they're all the same, and I do it to get the average over that 60-degree period there. So there we go. I've got my average, just simply comes out there. I believe that's in the data.
Something else.
Ripple voltage, again, we know the angles here, we know that angle, we know that angle, the drop is the same over here. So it's just sine 60, 0.866, so the ripple voltage is the difference. So it's, whatever that is, 144, 0.144, 14.4% ripple. So that's pretty low already. What we will do is put a capacitor on it. Okay, I should probably stop there. We can plot the diode currents. We know what the coding is. We know what they're doing. We can plot then the 3 sine wave currents, and they've got this sort of square light. Now this is, by the way, what I mentioned before. This is what we call quasi-square or quasi-square current pattern. And it's the same as the square wave, except that it's got no third harmonics in it. We've lost all the thirds due to symmetry. Okay, we'll come back to that next time and just finish that off. And then we'll do a lot of